In this video, we're going to review chapters 8 and 9 for the final review. If you remember, chapter 8 was about polar coordinates and a little bit about complex numbers, and then chapter 9 was about vectors. So for our first question, we're going to plot the point that has the given polar coordinates. So if you remember, this is just a different way of graphing things than the normal XY plane that we're used to. So when we have a polar point, it's of the form r comma theta, where r is a radius and theta is an angle. So for the point 2 comma 2 pi over 3, we would go out a radius of 2 and then around the circle until we hit the angle 2 pi over 3, which would be somewhere about here. And so our point should look something like this. And if we look at our four answer choices, the only one that looks like that is this one down here. Next, we want to give two other polar representations of this point, one with the radius less than 0 and one with the radius greater than 0. So I think the easiest one to take care of is probably the radius greater than 0, so we need another point with a positive 2 in the first coordinate. And the way we do this is all we need to do is get another name for our angle. So if we have a radius of 2 and we want to still have our angle at 2 pi over 3, we just need to find another name for 2 pi over 3. And I think an easy way to do that would just be to add 2 pi to it. So we could do 2 pi over 3 plus 2 pi, which is 2, and then when we want to add the two angles, we would have 2 pi over 3 plus 6 pi over 3, which would give us the point 2 comma 8 pi over 3. For our point with the radius less than 0, we want the radius negative 2. So what this means is we're going to count on the negative x-axis first. So this is negative 1 and this is negative 2. So if we consider that radius and we want to go around to our point, we're going to be moving in a clockwise direction. So our angle would be negative, and we're moving a total distance of pi over 3. So our point would be negative 2 comma negative pi over 3. In the next problem, we want to find the rectangular coordinates for the point whose polar coordinates are given. So again, this is another polar point, so it's r comma theta, and we want to convert this into rectangular coordinates. So we're going to use the formulas x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. So our radius is 3 square roots of 2, and then our angle is negative pi over 4. So we're going to just sub that into our two formulas. And then from your unit circle, the cosine of negative pi over 4 is square root of 2 over 2. So we're going to sub that in. So we have 3 times the square root of 2 times negative square root of 2 divided by 2. Oh, sorry, this one should be positive. So if we multiply that, we have 3 times 2 divided by 2, which is just 3. And then if we go and do our formula for y, the sine of negative pi over 4 is negative square root of 2 over 2. So we have, again, negative 3 times 2 divided by 2, which is just negative 3. So if we were going to write this as an xy point, we would have the point 3 comma negative 3. In the next problem, we want to take a rectangular point and convert it into a polar point. So the first thing to notice about this point is that it would be in quadrant 1 because both the x and y coordinates are positive. So when we find this polar point, we want our radius to be greater than 0 and we want our angle to be between 0 and 2 pi. I think the positive radius will come out kind of naturally, but with theta, all that means is we only need to consider angles in that first rotation of the unit circle. So how about we find the radius first? So radius is going to be the square root of x squared plus y squared, which is the square root of the square root of 8 squared plus the square root of 8 squared again, which if we simplify this, we get the square root of 8 plus 8, which is the square root of 16, which is just 4. And for our angle, we use the formula tangent inverse of y over x, which if we substitute in y and x, we have tangent inverse of the square root of 8 over the square root of 8, which gives us tangent inverse of 1. So finally, to evaluate tangent inverse of 1, I need an angle that has a tangent of 1 but is in quadrant 1. So the only angle that fits this is pi over 4. Alright, so if we write this as a polar point, then our point would be 4 comma pi over 4. And so that is our polar point. In this next problem, we're going to convert a rectangular equation into polar form. So we're given the equation x squared plus y squared is equal to 9. So I think for polar form, we want to get r's and thetas and no x's and y's. So we want to completely get rid of x squared and y squared. And I think when you first look at this equation, it should look like an equation that we talked about in class, which is this. So we had x squared plus y squared is equal to r squared. And so now, if you kind of compare this to the equation that we were given, we could conclude that r squared is equal to 9, which means that r must be equal to 3. So here, r equal to 3 is an equation whose only variables are either r or theta, and I know we don't have any thetas in the equation, but the important thing is that there are no x's and y's. So r equals 3 is a perfectly good polar equation that agrees with the rectangular equation that we were given. For the next problem, we're going to take a polar equation and then convert it into rectangular coordinates. So we're given the equation r is equal to 2 times the cosine of theta. So in the previous problem, we wanted to get rid of x and y and only have r or theta in our equation. Now we're given an equation with r and theta, and we want our only variables to be x and y. So we need to figure out how to get rid of cosine of theta and how to get rid of r. So I might start by trying to eliminate cosine of theta, and so I know that one equation with a cosine in it is x is equal to r cosine of theta. Now if I solve this equation for cosine, I'll get x divided by r is equal to cosine of theta. So this gives me a perfectly good expression to substitute in the place of cosine. So I can make this r equals 2 times x over r. So now I can start to solve this equation. Maybe I want to combine both r's, so I can multiply this r in the denominator to the left side and get r squared is equal to 2x. And now that I have an r squared, I can use another equation that I know and completely get rid of r altogether. So we know that x squared plus y squared is equal to r, so I can just substitute in x squared plus y squared in the place of r squared. And we get x squared plus y squared is equal to 2x. So this would be a perfectly good answer for an equation in rectangular coordinates. However, perhaps your final exam would want you to simplify this a little bit more. So a way we could simplify this a little bit more is we can get everything on one side, like this. So we'll have x squared minus 2x plus y squared is equal to 0. And then we do a little trick from algebra that we call completing the square. And the way this works is we pick a special number to add to our x terms that make it factor into a perfect square. So the way that we do this is we look at the number that's next to x. So in this case, we would have a 2. We would divide 2 by 2 and then square it. So 2 divided by 2 is 1. 1 squared is 1. So to both sides of this equation, I'm going to add a positive 1. And that's okay, because if I'm adding something to both sides, it's like it's not even there. So what this allows me to do is take the x terms all together and factor it as x minus 1 all squared plus y squared is equal to 1. And so this is the fully simplified version of the rectangular equation. Okay, in the next problem, we're going to sketch the vector indicated. So our indicated vector is this expression u minus v, and we're given the vectors u and v in a picture on this graph. So the first thing I would do is just translate this picture of vectors into a couple of formulas really quick. So from the picture, we can write that the vector u is, let's count our coordinates to the point. So we have -1, -2, -3, 1, 2, 3, 4. So the vector u is actually just the pair -3, 4. And remember that when we write vectors, we use those triangular brackets. So we can do the same thing for the vector v. And so if we count where the black point is on the right, we'll have over 1, 2, 3, 4, 5, 6, and up 1, 2, 3, 4, 5, 6, 7. So our vector v is the pair 6, 7 in the triangular brackets. So if we want to find the vector u minus v, we can take these formulas we found and just subtract them. So we talked about how to subtract vectors, and basically we just want to subtract component-wise. So what that means is we want to subtract the first component, so we'd have -3 minus 6, and we want to subtract the second component. So we'd have 4 minus 7, and this is going to give us -9, -3. So in looking for our answer, we're looking for the vector that when we graph it is -9, -3, and the only answer choice that fits this is this one right here. All right, for our next problem, we're going to be given a vector and we're going to find the magnitude and direction in degrees of the vector. So because the direction is in degrees, just make sure that your calculator is in degree mode. So we're given the vector 40, 9, and so the way that we find the magnitude is we use similar formulas to when we were doing the problem up here. Yeah, the problem up here when converting to polar coordinates. So for the magnitude of a vector, we're just going to take the square root of 40 squared plus 9 squared, which is the square root of 1600 plus 81, which is the square root of 1681, which seems like a really strange number, but if you plug this into your calculator, you'll actually find that it is a perfect square, and the square root of 1681 is actually just 41. So that's going to be the magnitude of our vector. And then the direction, we're going to use the tangent inverse formula again. So we'll have tangent inverse of 9 divided by 40. And here you can jump straight to using your calculator, and you should get 12.68 degrees as long as your calculator is in the right mode. So just make sure that it's in degree mode. All right, and for our final problem, we're going to recall the dot product and finding the angle between two vectors. So we're given the two vectors u is equal to 3, 0 and v is equal to 7, 7. And first we want to find u dot v. So remember that the dot product is just sort of a special multiplication that we do with vectors, where we multiply the component wise, but then we add those products together. So our answer is not going to be a vector. It's actually just going to be a number. So our answer is just a single number. And that's important to remember. Okay. So if we take the dot product of 3, 0 dotted with v, 7, 7, we're going to multiply 3 times 7, so we multiply the first two components, and we add to that the product of the second two components, which would be 0 and 7. So we have 3 times 7 plus 0 times 7, which will give us 21 plus 0, that should be 21. And so our dot product is just 21. And then finally, we're going to find the angle between u and v to the nearest degree. So to find the angle between two vectors, we use the formula theta is equal to the cosine inverse of u dot v over the magnitude of u times the magnitude of v. So we already know u dot v is 21 from the previous part, so we can go ahead and sub that in, and all we have to do now is find the magnitudes of the two vectors. So the magnitude of u is going to be the square root of 3 squared plus 0 squared, which is the square root of 9, which is 3. So we have 3 on the bottom. And then the magnitude of v is going to be the square root of 7 squared plus 7 squared, which is the square root of 49 plus 49, which is the square root of 98. So into our formula, we put the square root of 98 in the denominator, and now we have an expression that we can just plug straight into the calculator, and as long as you're in degree mode, you should get your answer to be 45 degrees. All right, so that concludes our review for chapters 8 and 9.